Okay, let me see. We have 6 people so far. Okay, any questions? I think we have 1 minute before the class hour starts. Does anybody have any questions? Let me put on my earphone.
Will lecture material from today be included on the exam?
No, I don't think so. Yeah. But if we do include anything, it will be very simple. Anything that we include from today's lecture, it will be very simple. So let's get started since it's 1:30. I guess let me ask if there's any question before we get started. Okay, so today I'd like to talk about Q of a cavity. Let me see. Okay. So today's lecture topic would be Q. Okay, let's see what the Q is. Q is the measure of the quality of a resonator. Q factor is also sometimes called the quality factor.
Oh, Professor, you're not sharing your screen.
Oh, I'm sorry. Let me see. I go and share the screen. Let me share it this way. Can you see my screen?
Yes.
Okay, good. You can see my screen, and I'm going to talk about quality factor of a cavity, which is also called a Q of a cavity. And it is a measure of how good the cavity is in terms of low loss. The lower the loss, the better the quality factor. Okay, so you can actually understand Q concepts by starting out with LC resonator. So if you have an LC resonator, so if we drive this with the voltage source, drive this circuit with the voltage source, you can use phasor technique to analyze this thing very easily. Then you find that the current is V over if this is C, this is L, the impedance of the circuit, okay, which is V times Y. Y is the admittance, which is 1 over the impedance, 1 over Z, okay? So this circuit will have a resonance. It will resonate when the denominator goes to 0. When the denominator goes to 0, can you check if my thing is recording? I cannot see from my side.
It's recording.
Okay, good. So when the denominator goes to 0, this thing is resonance, which means that Z or V goes to infinity. V becomes infinitely large, or Y becomes infinitely large, which means that you don't need the voltage source to create a non-zero current, okay? When that happens, when it's at resonance, you can switch off the voltage source. And V equal to 0, and yet you can have a current flowing in this circuit, and that is called the resonance current. And this happens when this is equal to 0, and you can easily show that this happens at omega naught equal to 1 over square root of LC. Okay, and that happens, then the current just sloshes back and forth between the inductor and the capacitor with this exchange of resonance energy. So if you were to now add a small resistor in this LC tank circuit, okay, you can again solve this problem using phasor technique very easily. You find that the current now is equal to V over J omega L plus R plus 1 over J omega C. Okay. However, there's a difference now because the denominator can never go to 0 with the real omega. If omega is real, the denominator is never equal to 0. So if you were to plot I as a function of omega, if you assume that the voltage is a constant, okay, if you plot this as a constant, and you will get this to be J omega L plus R plus 1 over J omega C. And that function would never go to 0. And if you plot I of omega, it will look something like this. Okay, if R is small, the place where this function peaks is when omega equals to omega naught. Okay, do you understand this so far? The resonance frequency is where this current would peak. And if there's no loss, the peak will go to infinity. It becomes bigger and bigger, okay? That is more or less denoted by this plot over here, that if you were to lower the loss of the circuit, the peak becomes bigger and bigger, okay, bigger and bigger. So that essentially is what a resonator is. It behaves in this fashion. And when there is loss, the signal actually is decaying with time. If you were to look for the natural solution of this circuit, so if you were to look for the natural solution of this circuit, you will now turn off the voltage and ask for when is there a current that can flow in this circuit. V is equal to 0 now. The current in this circuit would have to be something that goes as J omega T, but where omega R is the resonance frequency of this circuit, and we'll have a real part plus an imaginary part. Okay, there should be a, plus an imaginary part. And the imaginary part should be negative. okay, in order for it to be consistent. I think so, yeah. Sorry, it should be positive. Okay, so if you plug in this, then the current would be behaving like e to the j omega naught t e to the minus alpha t. It will decay with time. So due to the loss in the system, the current would decay exponentially with time. And you can say this of any other circuits. That is, if you have a cavity that is lossy, say if you have a microwave cavity, if there's no loss, then the resonance or the field in the cavity would oscillate forever. However, if you were to now open a hole or put in some kind of a loss in the system, then the resonance field will become smaller and smaller due to leakage of energy from the cavity mode, okay? So in general, what you can say is that when you have a cavity loss, so the electromagnetic field inside the cavity would be proportional to something like e to the minus alpha t plus a sinusoidal component. If you convert this to phasor, and if you put a R naught there, then the phasor would be something like this, okay? And that the magnetic field will also be behaving something like this. Okay, in general, the moral of the story is that any field that you have that is in free oscillation, this is in free oscillation. Okay, just like a swing in the park, if you let the swing just oscillate, it will decay to zero after a certain time. So what this says is that the energy in the system will become smaller and smaller. Okay, it will become smaller and smaller, saying that if the electric field energy storage, okay, should be proportional to e to the minus 2 alpha t, okay? If you take the time average of the electric field energy stored in this field, okay, this one would time average to a constant, but this one would become 2 alpha t times maybe W E naught or something like this. And then the average stored energy in the magnetic field would be W H naught e to the minus 2 alpha t, which means that the total energy in the cavity would be WE plus WT, and this is going to be a constant times e to the minus 2 alpha t. It's going to be a decaying signal. Okay, it's going to be a decaying signal. What is the Q? Q is the measure of how many times would the field oscillate before it decays to 1 over epsilon of its original value. If you look at this, okay, this thing is going to decay exponentially if the cavity is lossy. A Q is a measurement, is a measure of how many oscillations do you have in the cavity before it goes to 1 over E, its original value. So the Q essentially is a measure of, let me see, the measure of how many oscillations does it have before this thing decays to 1 over the original value. And then the energy is going to decay like 2 alpha t, okay? And then this will decay to its original value of 1 over E. If tau is equal to 1 over 2 alpha, or t is equal to 1 over 2 alpha, then this thing will become e to the minus 1, okay? And then you ask yourself, is the cavity is oscillating with a frequency of e to the plus j omega t at that resonant frequency. How many times must it oscillate before it decays to 1 over e of its value? So you take this tau, okay, take this tau value and then divide by omega, gives you number of cycles in radian. Okay, so Q essentially is the, let me see, do I have this right? No, I have it opposite way, which is that if tau is very small, so it should be actually tau omega over tau, okay? It's number of cycles in radian before the signal decays to 1 over e of its value. And then this tau is 2 alpha. Okay, this is number of cycles in radians before it decays. And this is what a Q is. Q is the number of cycles in radian of a sinusoidal signal, or decaying sinusoidal signal, before it decays to 1 over e of its original value. Okay, that is what the Q is. And this is an approximate concept, which is good for low loss. Okay, are there any questions so far as to what the Q is? Q is a measure of how many cycles the signal can oscillate before the energy decays to 1 over e of its original value. That time is given by 1 over 2 alpha. And with that time, if the signal is oscillating with a frequency of omega radians per second, this is the number of radians per second of number of cycles in radian before the signal decays to that value. Any questions about what the concept of Q is? Okay, so as I said before, if you have a cavity LC tank circuit, you can have things of different Q. Some circuit will have high Q, high quality if the loss is low, and then it will have small Q when the loss is high. And you can apply this concept, which is actually something that goes from circuit theory to cavity resonance as well. In the resonating cavity, there will be wall losses, and the wall losses can come from radiation, can come from dissipation in the metallic wall, and that will cause the signal in the, or the field in the cavity to decay with respect to time. Okay, so as I said before, you can use circuit theory to explain this, or you can use other kinds of theory. And in the cavity, we have to derive this alpha, the decay factor, sort of differently, because in a cavity, you can think of it as you have EM, electromagnetic stored energy inside. Okay, and then there will be wall loss on the wall. Okay, the wall loss will start to siphon energy from the main stored energy thing, and then the time average WT would decay with time. Okay, would decay with 2 alpha t W0, as we said before. Okay, but by energy conservation, this rate of decay of the time average energy stored, okay, must be proportional to the time average power dissipation on the wall loss. This is just an approximate concept. I would say that this should be an approximate concept, that the rate of decay, the rate of change of energy stored in the cavity is proportional to the negative of the power dissipation on the cavity wall, okay? But if WT is going to be of this form by our argument just now, then we know that ddt of WT is minus 2 alpha e to the minus 2 alpha t W naught, and this is just minus 2 alpha WT. Okay, this part is just WT. So you can see that there is a way of estimating alpha. Alpha is given by minus 1 over 2 the PD. Okay, the left-hand side is just PD, or minus PD. It's just, alpha is just then equal to PD, okay, PD over WT. So if there's a way for you to calculate wall loss, if there's a way for you to calculate the total energy stored in the cavity, you can estimate this decay constant. Okay, alpha can be estimated using this formula. Again, I want to say that this is an approximate concept. So any questions so far? So we define the concept of Q as the number of cycles of oscillations of the field before it decays to 1 over E of its original energy. You can also now use this way to define Q. And so since Q was defined to be omega over 2 alpha previously using our previous definition, okay, then we have a new formula for 2 alpha, and then now you have this to be equal to omega WT over PD. Okay, because we just show you the alpha is given by this thing, or 2 alpha is given by this thing. So you plug in the value of 2 alpha, you get a new formula for Q. Okay, and the interpretation is the same. It is the energy dissipated within a number of cycles that you have before the thing decays to 1 over E of its original value. Okay, so the more stored energy a cavity has, the higher the Q. The smaller the power dissipation, the higher the Q, and also the higher the operating frequency, the higher the Q. Okay, so in optics, you can have Qs of a few millions, whereas in microwave, it's harder to get Q that is that high. And also in microwave, you would want to increase the stored energy. So the larger the cavity, the higher the Q, because then the ratio of wall loss to cavity energy stored becomes smaller. Okay, are there any questions so far regarding the concept of what a Q is? Okay, so now that we know what a Q is, and if it were to plot it, it's going to look something like this, as I said before. Okay, and we can use our insight from the LC tank circuit to actually relate the Q of a system to the bandwidth and the pole location. Okay. So we can use back our LC tank circuit as the inspiration again. You can think of the functions that we have, which we call Y, to be our transfer function. This is the output, this is the input. This is our transfer function Y, okay? Y would be a transfer function in this system. So using that in electrical engineering, we usually call a transfer function H, but the transfer function that we have now is plus 1 over j omega c. Okay, and then you can show that this thing actually has two poles, but in the vicinity of the pole, I can approximate this as being a constant over omega minus omega r. Okay, omega r is a complex number. Can you see this, or you need me to elaborate on this? That in the vicinity of the pole, there are two poles in this system, but in the vicinity of the pole, I can approximate the function as such. And if you are not clear as to what I mean, I can show it to you. So the denominator, the y, or the y inverse, which is my z, is j omega L plus r over 1 over j omega c. And then you can multiply this through by j omega c, you get the omega square LC plus j omega RC plus 1 over j omega c equal to, if you want to look for the zeros of this, then you can factorize this. This can be written as omega minus omega r plus omega r, okay, over j omega c. And in the vicinity of the pole, say we are very interested in the omega being very close to the resonant frequency, or being one of the pole locations, then you can say that this is approximately equal to omega minus omega r. And then here you can replace with a 2 omega r, because you're in the vicinity. So omega is very close to that, and only this one would vary very rapidly, okay? And then you have j omega rc. So essentially it's approximately a constant, okay? And what I mean here is that because it's approximately a constant times this, you can show that the y of omega can be written as approximately a constant divided by omega minus omega r. Okay? So when omega is very close to omega r, the rest you can approximate with a constant. Is this clear to everybody? So in the vicinity of the pole, you can simplify the function to look only like this. Okay? And then you know that omega r is complex for this circuit, so it will have a omega naught minus j alpha, okay, plus j alpha. It will have a complex resonance, and then so y of omega is approximately equal to omega minus omega naught minus j alpha, okay? So this is a complex number, and if you were to plot this transfer function as a function of omega, if you were to plot this amplitude, where do you think it would peak? Where would it peak? If you just stare at this function long enough and ask yourself the question, where would the peak be? Alpha is a small number. Alpha is lost. Okay, alpha is small. Okay, we assume the system to be low loss. Where would this function peak?
So omega naught.
Very good. Okay, when omega equals omega naught, okay, this function would peak. Okay, if you plot it, it will look something like this. Okay, and then if you've done body plots in your undergraduate days, you probably should be quite familiar with this. Okay, and then so when would the half power bandwidth is? So we go through this complex plane analysis and say that if omega on the complex plane, you say that, well, omega real, and then imaginary omega, and then the pole location is given by omega naught plus j alpha. Okay, so it peaks when the operating frequency, which is real, is very close to the pole location. That is where it peaks. And then it will drop to 1 over, and if this length is alpha, okay, this length over here, you can do trigonometry. This length here will be square root of square root 2 of alpha, okay, square root 2 of alpha. And then if you're over here, omega plus delta omega, then you can easily work out that the peak would drop to half its power bandwidth. This is called a half power point because it's 1 over square root of 2, and it would drop to 1 over square root of 2 when omega is equal to omega naught plus delta omega, okay? And if that delta omega is given to be 1 over root 2, you can show that the bandwidth, you can show that, let me see, I have worked out the formula for delta omega. Delta omega is 2 alpha, okay, delta omega. Let me see, in the lecture notes, I have this delta omega over 2, this delta omega over 2, and the other point is minus delta omega over 2, okay? And then the bandwidth of the whole thing is delta omega. And you can show that delta omega should be about, let me see, delta omega should be about alpha, okay? Delta omega should be about alpha. Oh, sorry, delta omega over 2 should be alpha. If this is alpha, this point here, where it drops to half power bandwidth, is alpha. Okay, this length should be equal to that length over there. Okay, that is alpha, so this must be the alpha. So it means that the bandwidth is 2 delta omega. Okay, the bandwidth is, sorry, you can finally work out that delta omega is 2 alpha. Okay, by just using the techniques that you have learned from Bode plots. Okay, that if you just shift slightly over to the right and slightly over to the left, you will reach the half power bandwidth point and figure out the bandwidth of the signal. And so you can also show that the Q is related to omega over naught over 2 of alpha, but you can show that 2 alpha is actually the bandwidth. Okay, 2 alpha is the bandwidth, as you can see from this picture over here. 2 alpha, if this is alpha, 2 alpha is the bandwidth, and hence you can also write this as omega naught over delta omega. So if you know the bandwidth of the system, and if you know its resonant frequency, you can also find the Q. The Q is resonant frequency divided by the bandwidth of the signal, of the system. Okay, is this clear? So this is a good rule of thumb to understand the relationship of the Q to the bandwidth of the system. Okay, so right now let's go about discussing how we can calculate this loss. Okay, this loss, this decay factor, as we said before, can be calculated many ways. And in the case of resonating cavity, it is given by PD over 2WT, okay, in the cavity. In a RLC tank circuit, of course, you have a closed form formula. You can go to RLC tank circuit and solve this equation in closed form. But for a cavity, for an electromagnetic cavity, we don't have that liberty of having such a simple formula. However, we have this relationship between cavity loss and the decay factor using this energy conservation argument. So if there's a way that we can find the wall loss, PD is also called a wall loss or the cavity loss. Okay, then we can find the energy stored in the cavity quite easily. Okay, because we know how to find the electromagnetic field inside the cavity when there's no wall loss. So this is going to be a perturbative concept. Okay, perturbative concept in the sense that WT is the same as that of the lossless case. We assume that the wall loss is small, so that even when we have the loss, the energy stored in the cavity does not change very much. We already know how to look for the modes of a rectangular cavity. Okay, we can get those electromagnetic field and find this very easily. The only thing that we have not learned how to find is the wall loss. How do we find the wall loss? I'm going to discuss that next. Okay, we're going to use Poynting's theorem to find the wall loss. Okay, we're going to find the wall loss by invoking Poynting's theorem. We integrate the wall loss over the surface of the cavity and then take the real part of the Poynting's vector. Okay, and then dot with the normal of the cavity. Normal of the cavity is a unit normal. Okay, for this, for any cavity, it will be a, let me put n that way. Okay, so it will be a wall loss representing the time average power flowing in the direction normal to the cavity wall. Okay, so this is the expression for the wall loss in an electromagnetic cavity. How do we find this expression? Well, I would like to rewrite this equation using the cyclic formula that A dot B cross C is equal to C dot A cross B is equal to B dot C cross A. Okay, then I can recycle this or make it cyclical and write the power dissipation, the wall loss, has been equal to half the real part. I can take the real operator out, and then the surface integration. I can put n cross E dot H star over here, ds. This is, in a sense, more intuitive. And you note that what is n cross E if we have a PEC wall? If the cavity is made of PEC, what is n cross E on the cavity wall? Anybody? Anybody? What happens to the n cross E on the cavity wall? If this cavity is made of a PEC wall, what will happen to n cross?
E is parallel to the cavity wall and n is perpendicular. So their cross product will be parallel to the cross to the wall, and so it should be 0.
Yeah, but I think I heard you say something wrong. So if you have a PEC wall, okay, this is PEC. Is electric field normal to the wall or parallel to the wall?
Yeah, it's parallel to the wall.
It is? If you have a PEC wall, how does the electric field behave around the PEC wall?
Well, according to the boundary conditions, we know that the electric field tangential components are equal, but they equal to 0 because we have no electric field in PEC.
Right.
So we have only a perpendicular component.
Right. So the electric field should be normal to the surface, not parallel to the surface.
I agree. I was saying that the perpendicular, the
electric field should look like this. Okay. So n cross E should be 0 on the PEC. There's no tangential component. So this is like a sanity check in the sense that if you have a PEC wall, there's no power flow into the wall. Okay, this is like a sanity check that we use to look at a formula. And it's only non-zero for a non-PEC wall. A non-PEC wall would have some losses. So then what you need to do then is to actually estimate what this n cross E is, okay? But there's something that I like to mention, that in the cavity, for instance, you assume bouncing wave, okay? And one thing I want you to note is that if you have a plane wave incident on something that has very high conductivity, okay, this is a PEC, sigma is going to infinity. What happens is that the K vector, the beta vector, okay, beta vector will become very large, okay, will also go to infinity. Okay, because beta square is omega square mu epsilon, but we have a complex permittivity over here, and that permittivity is real plot plus j sigma over omega. Okay, sigma becomes very large, and beta square just becomes extremely large. Okay, it becomes extremely large, and this would be omega square mu j with a minus sign here. Okay, sigma over omega, but it just becomes very, very large. So when beta becomes very, very large, okay, by phase matching, this beta must be almost normal to the surface, okay, because of the phase matching condition, just as ordinarily that you find when the permittivity or the conductivity of the medium is very large. The transmitted wave must be very close to be normal. Okay, this is almost 90 degrees, okay? And this is due to the phase matching condition. Hence, you can assume that any wave that bounces off the wall, the transmitted wave will propagate normal to the surface, okay? The beta vector is going to be like that. And you can assume that you have a plane wave propagating in that direction. And in that case, you can say that, well, you can say that n cross E is related to H tangential by just that intrinsic impedance, okay? The eta of the metal, which is the mu over epsilon T, okay? Epsilon of the metal. And as I say, the epsilon of the metal is becoming something very, very large. And if you can look into this, then you find that n cross E is HT times, if you put in the approximation that sigma is very large, then this is going to be multiplied by something that looks like omega mu over 2 sigma, okay? And then 1 plus j. Okay, if you plug this in and assume that sigma is very large, you're going to get this approximation, which means that n cross E becomes very small when sigma becomes very large. Okay, and using this approximation, you can make and you can plug into this expression and derive an integral that PD would be equal to with the approximation of a PEC wall I'm not going to go through the detail, but with the sanity check that when sigma goes to infinity, this wall loss is equal to 0, okay? This tends to 0 when sigma goes to infinity. This is the wall loss. And so if you can estimate the tangential magnetic field on the wall, okay, if you can estimate the tangential magnetic field on the wall, that is not too difficult to do because the tangential magnetic field was not 0 on the PEC wall. Okay, you remember that when you have a PEC surface, say if this is PEC, the magnetic field has to go something like this, okay? H is behaving like this with no normal component. You can take the magnetic field of the cavity before you introduce wall loss and use that to estimate this number. Okay, then you will have a good estimate of PD, and then of course WT you can find by using twice the energy of the storage in the magnetic field. It should be the sum of the electric field and the magnetic field, but for a resonating cavity, those two are equal to each other, just like the energy of a tank circuit, okay? So you can calculate this using the lossless case, using the cavity with the lossless case, and then you can actually finally get the Q to be something like, after you plug in all the formula, okay, and you integrate the magnetic field over the volume over the wall loss, which is proportional to the tangential magnetic field on a surface, and that you have this formula. You can work it out to be something like 2 over delta volume integral, okay, plus the surface integral. And delta is a skin depth that we have learned before. When you have a metallic surface or metallic medium, the field can only propagate exponentially inside the medium, and it decays in a distance called the skin depth. And you can identify that this is somewhat related to the skin depth and write the right-hand side as such. So any questions so far? So this is how you would find the Q of a cavity if you know the electromagnetic field inside, as you know the tangential magnetic field on the wall, okay? And the lesson learned here, some physical insight you can gather from here is that, well, the Q is proportional to the volume times the surface area times delta, okay? Because the numerator is a volumetric integral. So the numerator should be proportional to the volume. The denominator is a surface integral accounting for the wall loss. Okay, so it should be proportional to the surface area of the cavity. And then there's the skin depth formula here. So what this formula tells is that the larger the volume of the cavity, the higher the Q. Okay, the smaller the surface area the cavity has, the larger the Q. Okay. The smaller the skin depth, which means that you are close to being a good PEC. Okay, if you make the cavity out of good conductors, then the wall loss would be small. Okay, and then the Q of the cavity would be very large. Okay, so this is the kind of intuition you can develop. Okay, so I can go through an example with you, but it is pretty straightforward. You want me to go through an example, or should I just skip it? How do you apply this formula? Or do you guys want to see an example, or you want me to skip that?
To me, it's clear.
What?
To me, it's clear.
It's clear, right? You know, this is a lot of plug and chug. We call plug and chug in engineering. You find the expression for the numerator, you find the expression for the denominator, you plug in this formula. And I can just briefly discuss the example. Okay, and say the lowest mode that we have in a rectangular cavity is the TM110 mode, okay? TM110 mode is the lowest mode in the cavity. And you can think of this mode as being a truncated rectangular waveguide. If I have a rectangular waveguide, okay, this is the z direction. The mode that you can have propagating in the z direction is TM11 mode. Okay, TM11 mode would be the wave that bounces back and forth around like this. Okay, you can say it propagates in or bounces in different directions. And this is the TM11 mode. And the magnetic field is transverse. Okay, if you look at the top, you will see that the magnetic field is, maybe I should draw the magnetic field. If I look at the magnetic field from this side in, the magnetic field should look like this. Okay, because magnetic field cannot end on a waveguide wall, on a PEC wall. Okay, and then if you short this waveguide in the front and in the back, you will short out the electric field. But the electric field for this mode is perpendicular. So if I take a top view, electric field is like this. Okay, but if I just look from the top, electric field is like this, and electric field is pointing out of the paper in this mode. Okay, so it doesn't matter if you put a shorting plane in the front and the back of this cavity, electric field will not get shorted out because the electric field is normal. Okay, this is the z direction. Okay, so hence you can make this mode into a cavity mode by just shorting the front end and the back end of this cavity. That is the TM110 mode. And since it's a TM110 mode, you can characterize it with EZ not equal to 0. And EZ is given by E0 sine m pi x over a, and then sine pi y over b. Sorry, this m should be 1. Okay. TM110 mode. So there's no variation in the z direction. Okay, partial z equal to 0. Okay, so this is easy, and from EZ you can of course plug into Maxwell's equation. You find your Hx, you find your Hy, and then with the Hx and Hy, then you can find your HdV. Okay, over the volume of the cavity. Okay, and then you can calculate this. It's done in the lecture notes. Okay, this is a straightforward calculation. And then the next thing you need to do is to calculate the denominator. The denominator would be the surface field. If you look at this cavity, there'll be tangential H field and tangential E field, and you can calculate them at different surfaces. Okay. So it's done in the lecture note as well. I won't go into the detail, but it's straightforward plug and chuck calculation. Okay, you can do this as well. ds over the cavity wall. There will be 6 walls, but they are in pair, and you can see that you need to actually go through the three sets of walls, because 2 of the walls are very similar in character, and then you go through that. And the formula is finally given in the lecture notes. Okay, I won't go through the detail unless you want me to show you the detail. Any questions so far? So finding the Q of the cavity is not as simple as finding the Q of an RLC tank circuit. It's slightly more involved, but there are ways to do that. There are formulas for you to do that. Okay, so if you ever become a microwave engineer, or if you become an optical engineer that needs to calculate the Q of a cavity, you will have to estimate the cavity loss compared to the total energy stored in the cavity. And from that, you can find the Q. Okay, if there are no more questions, I'd like to talk about mode orthogonality next. Okay, I'd like to talk about mode orthogonality. This is important. I find that you often find that all the modes of a waveguides are orthogonal to each other. And as I said before, a waveguide problem is actually an eigenvalue problem. Say, for instance, if you write down the waveguide problem, we often say that, well, the piloting potential might look something like this. Okay, might look something like this. And if we write this more suggestively, okay, it can be written like this. Okay, and if I write a matrix eigenvalue problem, then that would look something like this. This is my matrix eigenvalue. You can see the parallelism or the homomorphism. This eigenvalue is the same as this eigenvalue. A function can be thought of as a vector. Okay, a Laplacian operator that I have can be thought of a matrix operator. And then this can also, again, a function can be thought of as a vector. So if I can prove to you that the eigenvectors of a matrix system is always orthogonal, it will be quite easy to prove to you as to all the modes of a waveguide are orthogonal to each other, and that can be actually proved. Okay, so let me start with this equation. Let me multiply this equation with let me see. Let me first by assuming the A is summation. A summation means that A conjugate transpose is equal to A. Okay, A conjugate transpose is equal to A. That means that A is summation. Okay, this is something that you should have learned in linear algebra. And so if A is summation, then I can multiply this equation with BI conjugate transpose. Dot multiply. Then on the left-hand side, I will get BI times VI is equal to lambda I BI conjugate transpose BI. Okay, I will have this as my equation. And what do you know about the left-hand side? If VI is the same for both ends of this left-hand side, and you conjugate transpose it, and if A is summation, what do you know about the left-hand side? Does anybody not have linear algebra before coming to this course? Does anybody not have linear algebra? I suppose everybody has linear algebra. Okay, so tell me what the left-hand side would be if A is summation and this is the conjugate transpose of this. Okay, and maybe I ask you a simpler question. What would be the right-hand side for this BI conjugate transpose dot with BIB?
Wouldn't it be the magnitude of VI squared?
That's right, magnitude of VI squared. And what do you know about it? Is it real, imaginary, complex?
It's real.
It's always real. Okay, this thing is always real. Okay, another property of a Hermitian matrix is that this thing is also always real. Okay, it's written in most linear algebra book. I can prove it to you easily, but I don't want to spend the time proving it. So if this is real, the eigenvalues are always real. Okay, so the eigenvalue of a Hermitian matrix system is always real. Okay, it turns out that you can prove that this operator is Hermitian. Okay, very similar to that this matrix A is Hermitian. And then you can show that all the eigenvalues that you have in the waveguide modes are always real. Okay, that I will not prove to you, but it's something that I'd like you to know. Okay, and also I want you to prove that different eigenvectors are orthogonal to each other. Okay, so if I have two eigenvectors, say this one satisfy this equation with this eigenvalue and eigenvector. And then I have a second eigenvector satisfying this equation with eigenvector Vj. Okay. Then I can multiply this equation with Vj conjugate transpose with the dot product, and multiply this equation with Vi conjugate transpose. Okay. And can you see that Vi conjugate transpose dot of A dot of Vj, is this a scalar number or a complex number? I mean, is this a scalar number or is this a vector? When you take this inner product, what does it become in your linear algebra course? It becomes a
scalar.
It becomes a scalar. Very good. Okay. So if I have a scalar number, and if I were to take its transpose, okay, conjugate transpose, and in linear algebra, when you take a conjugate transpose of three matrices, it will be given by this. Okay, you probably know this rule in linear algebra. Okay. In other words, in linear algebra, if you have three vectors A or three matrices, or if you transpose them, it will be equal to this times A. Okay. And using this rule, you can prove the both things quite easily, except that you have to add the conjugate transpose to things. Okay. So if this is true, then what I'm trying to get at is that the left-hand side, okay, I also have a Hermitian matrix here, so this is equal to that. So the left-hand side of these two are actually the same as each other. Okay, the left-hand side of the two are actually the same as each other, and that I actually take the conjugate transpose. I get the left-hand side to be the same as each other. The right-hand side, I also would take the dot product and take the conjugate transpose. Okay, so if I subtract the two equations, because the left-hand side is equal to each other, I get 0. And then since the eigenvalue of the system is real, okay, for the first equation, I get Vj transpose dot Vi, okay, minus lambda j V j transpose dot Vi, okay? Because I take the product and then I take a conjugate transpose. I take the product and conjugate transpose, I get this thing. I assume that lambda j is real, okay? Then I will have this thing, Vj conjugate transpose dot Vi, okay? And this has to be 0 because left-hand side subtracts to the 0. What means is that if lambda I is not equal to lambda j, these two must be orthogonal. Okay, the eigenvectors of a matrix system with Hermitian operators are always orthogonal, and hence you can prove quite easily that if this operator is Hermitian, okay, this operator is Hermitian, which is over here. If this operator is Hermitian, all these eigenvalues will be real, okay? So I like to draw this parallel, but I probably have not convinced you that this operator is Hermitian, okay? It takes quite a bit of doing, but I can provide you the proof in the lecture notes, okay? I can provide you with the proof in the lecture notes. But the next thing I'd like to discuss is the fact that functions are vectors. So I say that this thing that I have here, okay, is analogous to an operator multiplying by a vector x. So what I'm thinking here is that this is a vector. Okay, this is an operator. This operator is very similar to the matrix operator in the sense that the matrix operator takes a vector and give you a new vector. So A maps from X to Y, okay? So it's an operator in the linear algebra sense. And you can also say that, well, this thing can be thought of as f of Rs. And if this is a vector, this is also a vector, okay? So then this is a vector that maps size of S Rs to f of Rs, okay? So why is it that we can think of a function as a vector? You probably would never taught to think that way in any of your courses before. Well, think about if you have to do a computation. Say if you have to do a computation, say, with a very simple function. The function is a vector, okay? And if you were to do computation with this function on a computer, you would digitize it. Function is something like this, and it's a continuum function, so it takes infinitely many numbers to represent this function. However, in the real world, when you go to the computer, you probably digitize it. And then you would digitize this function at certain location, okay? And you might call this x1, x2, x3, and so on, maybe xn. So in the real computer, if you are into signal processing and if you have to work with the computer, you have to digitize things. So a function has to be stored as a column vector. Okay, so this would be stored as a column vector in the computer. So you can think of any functions of x can be thought of as a vector. But what about a function of x and y? It goes into the display mode. Why does it go into this mode? Okay. So you can also think likewise that if I have any function of x and y, if I need to store on the computer, okay, I will store the value of this function over discrete points. And then this will be stored as xi, yi. And again, this will be stored as a column vector, if you want to think of it that way. So all functions can be thought of as a vector, and you can even think about a three-dimensional function. Ultimately, when you need to store it in a computer, okay, you would discretize x, okay, you discretize z, and this will become a vector in the computer storage. So you can think of all functions as being vectors, but vectors in the continuum sense, in the sense that in the truth matter, in the actual fact, you need infinitely many numbers to represent this function. But in practice, you use a finite number of points or data points to represent this function. So whatever we do on a computer is very similar to what happens in linear algebra. So if I were to think about inner product, like in linear algebra, I think of this as an inner product, okay? This is an inner product, and I would write it as bi, the L component of this vector, okay? times Bj, the L component, L equals to 1 to n. Okay, if I store this as a vector, then the inner product is defined to be that. And then now you can define inner product between two functions, fj, or psi j and psi I, as being equal to the sum over the cross section of the waveguide psi a r s psi j r s. Okay, so the two look very different, but in practice, if you were to implement this on a computer, you will replace this with a discrete sum. Okay, not I and j, but L and M maybe. Psi I, R, L, or maybe I can say X, XL, YL, YM maybe. Let me see. Is this right? Yeah, LM, psi J, XL, YM. Okay, I can think of this as an inner product implemented on a computer that way. And if I store this as a column vector, and this as a column vector in a computer, this is very similar to taking a vector I dotting product with a vector J. Okay, so when you implement an inner product on a computer, it is very similar to what happens in linear algebra. Okay, so hence this thing can be thought of as a kind of abstract inner product. Okay, abstract inner product, and you can define norms for such inner product as well. So the proof is rather long, but let me just outline it somewhat. That how would I say, if I can prove that this function, if this is Hermitian, then I can show that all the modes that can come from this equation, okay, that comes from this equation, all the modes that come from this equation have to be orthogonal, very similar to what happens. So you will have to define what a Hermitian matrix is in the language of using inner product. So in the past, when you learn what a Hermitian matrix is, you learn it differently, but now we have to use a different way to define a Hermitian matrix. Hermitian matrix Xi, okay, if A is Hermitian, okay, and if I were to take the conjugate transpose of this dagger here means conjugate transpose, it would be the same as let me see. Okay, so if I take the thing, and if I use the rule of linear algebra, this would be just equal to that. Okay, I'm using the rule of linear algebra that A dot B dot C transpose is equal to C transpose dot B dot A transpose. These are all matrices. Okay, these are all matrices. Okay, so if I take this rule where a dagger just means A transpose followed by a conjugate transpose. Okay, this is called a conjugate transpose. Dagger is equal to conjugate transpose in linear algebra. So in the conjugate transpose, you take the transpose and then you take a conjugation. Okay, if I apply that, I get this first equality. And then because A is Hermitian, I would get the fact that this is also equal to xj conjugate transpose dot A dot xi. Okay. Let me see. Let me see if I get it correct. If I take the conjugate transpose of that, I get that, and that should be equal to that. And then so let me see. So you can use this property, the inner product property, to define what the Hermitian matrix is. So if this equals that, okay, if this inner product equals that inner product, okay, that means that A is Hermitian. So we can use the concept of inner product to define Hermitian property of the thing. And you can go through this as well. It's kind of a long proof. I'm not going to go through here. And then you kind of write things in terms of inner product now, okay? That if you have this thing, and if I want to prove this to be Hermitian, I will go through an inner product proof and show that that thing is Hermitian. I guess I'll stop here because this proof is something that I would not hold you to in this course, but I just want you to know that orthogonality of modes that we see in the waveguide or cavity is related to the orthogonality of eigenvectors in the matrix eigenvalue problem. Okay, that connection is kind of difficult to see at this point, but I just want you to have this as a background knowledge. Okay, so let me stop here and ask if you have any questions regarding this. Okay, my thing is not responding. Okay, so let's regurgitate what we studied today then. We studied about the Q of a resonator. We try to get intuition by looking at the Q of an LC tank circuit. You say if you have a LC tank circuit, well, you have resonances, and if there's no loss, then the resonance frequency is purely real. Okay. However, if there's any loss in the system, the resonant frequency is never real, and hence the denominator would never go to 0. And if you plot this transfer function, it will look something like this. And we can also look at an LC tank circuit and say that, well, if you were to take away the source, taking away the source in an RLC tank circuit is like looking for the homogeneous solution of an ODE. Okay, you can formulate this problem in terms of ODE. You take away the source, it's the same as setting the right-hand side of the ODE to be 0. It's like finding the homogeneous solution. The homogeneous solution of this system is also called the natural solution or the free oscillation solution. Because of the loss, the free oscillation would be complex, okay, which is actually the pole of this system, and hence the current on this system will be decaying. And by the same token, if you have a cavity, if it has wall losses or it has leakage losses, the free oscillation in the cavity would also decay with respect to time in such a manner, okay? But because the free oscillations in the cavity has to decay with respect to time, the energy has to decay as 2 alpha t because of the squaring of the field. Okay, the field is proportional to this. The energy, which is proportional to the square of this quantity, is 2 alpha t. And you have this kind of property. And the Q is just a concept of counting the number of oscillations in the cavity before the energy decays to 1 over E of its original value. So if the energy is decaying in this manner, it will decay to 1 over e in this time interval. Okay, t equal to tau, and you count the number of cycles that goes on after this interval. You just divide omega by tau. So Q is a measure of number of cycles in the cavity or in any circuit before the energy in the system decays to 1 over E of its original system. So you can look at the Q of a circuit. The transfer function becomes highly peaked when the Q is high and so on. You can also use this concept to define the Q for cavity, and hence you can also relate by energy conservation. The decay factor of a cavity is proportional to wall loss divided by the total energy storage. Okay, because of this very nice formula, we have a handle on how to find the decay factor alpha. Okay, so these are just how you would find this decay factor, and once you found this decay factor, you can show that this decay factor is related to the bandwidth of the system. I use a very simple RLC tank circuit to show that the bandwidth and the pole location are very much related to the bandwidth of the system. Okay, as long as you can approximate the transfer function of the system by a single pole. Okay, when that happens, you can do that. And you can also do the same for a cavity resonator, because you can think of the resonance as the pole of the system. Okay, and here I just went through the rigorous mathematics, electromagnetic field theory, to find out the wall loss. The wall loss is given by this formula. And then after some manipulation, you find that the wall loss is given by that, and you can find the total energy stored in the field. You can actually calculate just the magnetic field because the energy stored in the electric field is the same. Okay, and then you plug this in, you can use that example of a TE or TM110 mode of the rectangular cavity as a test case and find the Q of the cavity. And then I want to drive this point into your mind, which is that the fact that all these modes are orthogonal is very much related to the fact that eigenvectors and eigenvalues or Hermitian matrix system is orthogonal. Okay, and then I want to try to relate this to a matrix vector product, similar to a matrix vector product. A function is actually a vector, and then an inner product is also expressible in terms of a functional inner product. And then you can define conjugate transpose in this way. And I kind of stopped there, okay? I stopped here because I don't hold you responsible for this knowledge. I just want you to know that the linear algebra concept of orthogonality of eigenvectors is very similar to the orthogonality of modes in the cavity and the waveguide, okay? And maybe sometime in your career, you might want to read that out, okay? But I would just have you know this as a fact at this point, okay? Any questions? If not, then I just let you go, okay? I just let you go.
Professor Chu,
Yes?
do we have an office hour today?
Yeah, I hold an office hour this afternoon. Maybe I do it at 3:05. Let me take a break first, okay, before I have to